In this video, I'm going to go over the quizzes we had in the class. This is useful for your final exam. So the first question, two identical tiny spheres have the same electric charge and the force between them is 10 Newton. If the electric charge on each of them is doubled and their separation is also doubled, the force each exerts on the other will be, so we know the formula F equal to, sorry about that, let me see. Okay, the formula for that is F equal to K Q1 Q2 over R square. This value is 10. Now what is he saying? Now Q1 is doubled, so let me take this as F1. Now F2 equal to K times 2Q1 2Q2 over distance is also doubled 2R square. Is that right? So F2, can I say that as 2 get cancelled? 2 square, which is 4. So 2 times 2, which is 4, divided by 4, they get cancelled. Can I say F2 is same as F1? So that must be 10 Newton. Now the second question, a metal sphere 1 and 2 are touching, both are initially neutral. The charged rod is brought near. The second point is the sphere are separated. The charged rod is then removed. Afterward, the charges on each sphere are. So if you look at it, the charged rod is brought near. So once we have this positively charged rod, bring it to the near, what happens? All the negative charges are going to be come closer to this. All the positive charges are going to be right there. Now what we did, we separated those two. So now still this one is going to have positive, this one is going to have negative, and rod or sphere 2 is going to have positive charge. So the charges are going to be, basically you can see Q1 is a negative and Q2 is positive. Third question, identical metal spheres are initially charged as shown. Spheres P and Q are touched together and then separated. So here when we touch these together, P and Q, what happened? The total charge they have plus 4 nanocoulombs minus 2 nanocoulombs. What happens here? Now they get cancelled out. 4 minus 2. The rest of the charge is only positive 2 nanocoulombs. That positive 2 nanocoulombs is going to be spread all over these two. So basically the P has 1 nanocoulomb of positive charge, Q has 1 nanocoulomb of positive charge. Then sphere Q and R touch together. Now this Q is, bring it closer to the R, okay, and that one has negative 1 nanocoulomb. So this negative 1 nanocoulomb and positive 1 nanocoulomb cancel out each other. So Q and R spheres will not have any charge left. So he's talking about what is the charge in R. It must be 0 nanocoulombs. Okay, fourth question, which of the following statement is true? Force and electric field are vector quantities. So we are talking about true statement for sure. We know force and electric field, both of them are vector quantities. Okay, fifth one, as shown, two particles, each of charge Q, are fixed at opposite corners of a square that lies in the plane of the page. A positive test charge Q is placed at a third corner if F is the magnitude of the force on the test charge due to only one of the other charges. What is the magnitude of the net force acting on the test charge due to both of these charges? So basically if you look at here, because of one charge he's talking about force acting on it is F. So everything is positive charge. Can I say because of, let me take this as Q1, Q2 and the small q. So let me take this as F2, force on this small q because of Q2 in this direction, and another because of Q1. Both of them are positive charges, it will repel each other, so that's F1. Now what is the resultant charge? Q1, Q2 are same. I mean, I didn't draw according to the scale, so this is my F2, that's my F1, so resultant force is going to be in this direction, right? So what is the magnitude of this? F1 and F2 are the same, it must be square root of F. We know that F1 equal to F2, so it must be square root of F. That's the total force acting on that charge. Okay, next one. Which electric field is responsible for the proton's trajectory? So a proton is moving in this trajectory. So which of the electric field is responsible for that? So we know that electric field always starts at positive, ends at negative. So assume that here is a positive charge, okay, and here is a negative charge. Okay, now this trajectory motion of the proton is going in this direction, like this. So which one of these are responsible? For sure it's not going to move in this direction, because if it is, the electric field is, in this choice, so there is positive charge there, negative charge there. If we leave a proton right there, it will directly go away. It's not going to go in the trajectory motion. For sure that's not the charge. I don't think we'll get this kind of motion with two charges, but I don't think this is responsible. But if you look at here, so this one is also not possible, because this is proton always repels, so it has to go towards the negative, not towards the positive. So if you look at this, I'm sure this is the responsible electric field, because here is the positive charge, here is a negative charge, right? So if I leave a proton right there with the initial velocity, it will go a trajectory motion like that. So this electric field is responsible for the trajectory motion. Next one, how many electrons make up a charge of negative 38 microcoulombs? So number of electrons, right? So number of electrons equal to charge over charge of the electron. So he gave you 38 microcoulombs over 1.602 times 10 to the power of minus 19 coulombs. That's the charge of the electron. So it is 38 micro over 1.602. Electron is negative charge, so I'm looking for number of electrons. I didn't put the negative charge there. So 38 micro over 1.602 times 10 to the power of minus 19, it will be like 23.72 times 10 to the power of 13 number of electrons are there in that amount of charge. Now, which of the following statement is true regarding two equally charged parallel plates? Both plates are uniformly charged and first plate carries the opposite charge of the other and separated by distance d. He's talking about capacitor. We know that there is always electric field between these two plates. It's constant everywhere between these two plates. Outside of these plates is 0. So electric field strength is 0 outside of the plates and present between the plates. Electric field strength between two plates is same as outside of 30. This is wrong answer. So look like this is the right answer. Let me read the C. I want you to go, even though if you find the answer in between, but please go through the remaining two also. Electric field strength is 0 at any point since charges are opposite. No, that's wrong. Electric field strength is there every point, but it is not equal. That is also wrong. Electric field, we found that electric field at any point in between the plates is same. So B is the right answer. Now, fourth one. What is the direction of electric field at the dot? So he's talking about what is the electric field direction right there. We know that electric field is a vector quantity. It has both magnitude and direction. So if you look at positive charge, because of the positive charge at this point, it's going away. Let me take this as E1 because it's Q1 and Q2. Now we know that electric field comes towards the negative charge. That's E2. So what will be the resultant field direction? It's going to be in this direction because the y components are going to cancel out each other. The x components add up. Now the last one in this quiz, two positive charges of magnitude q are each a distance d from the origin A of a coordinate system as shown. At which of the following points is the electric field least in magnitude? So we can use the same principle what we used up there. So at point A, because of electric field, because of Q1, it's going to go away in this direction. Because of Q2, it's going to go in this direction. And those two quantities are same because Q is same and distance d is same. So here I can say that magnitude is 0. Okay. Now at any other point I can see, say at B, because of this Q it's going to go in this direction. Because of this Q, still it's going to go in this direction. So both of them are going to add together. We will have some electric field there. At C also we have some electric field because of Q2 and Q1 we have electric field there. At E still we have electric field. It's going to be in this direction, in this direction. D we have electric field. Okay, so the point we do not have electric field is point A. Okay, here is the next example. The electric field strength including direction is given for the box. The box contains, it has positive charge and negative charge. So the numbers he provided here, those numbers are electric field in Newton per Coulomb. We know that electric field always starts at positive charge and ends at negative charge. Okay, that's the electric field. Now 15 Newton per Coulomb is going in, and 20 Newton per Coulomb is also going in. So we'll see what are the total electric fields going into the box. So I have 15. Here is one first 15, another 20, another 15. So 15 plus 15 plus 20. That's the total electric field going in. What is the total electric field going out? This is E in. E out is 10. So that's going out, 20 going out, and 15 going out. I don't know why I circled it first. 10 plus 20 plus 15. Okay. So this is 50. This is 45. So this is E out. Okay. So more electric field is going in compared to electric field coming out. So for sure this box must have a negative charge. Okay. Then only electric field, the net electric field is going in into the box. Okay. Next one, the electric flux through the shaded surface is, so here he gave us a square 2 meter by 2 meter, and it is making an angle 20 degrees with x-axis. We know that phi electric flux phi E equal to EA cos theta, where theta is angle between E and normal to the area. Okay, so here we need to find what is the angle between E and normal to the area. So if we look at here, so electric field is going on the, towards the x-axis. Now this normal, can I say it is around 70 degrees with the x-axis? Okay, so if you look at here, if this plate is perpendicular to the magnetic field, then we'll end up having more magnetic I'm sorry, more electric flux. We are talking about electric flux. Okay. So to get the, to find out the electric flux coming here, the theta angle between E and normal to the area, I would say that is 70 degrees. Think about it, you'll get it. Here, so EA cos theta, when I substitute that, I end up with 136.8 Newton meter square per coulomb. Okay. Third question, what is the ratio of VB over VA of the electric potential at the 2 points? So remember, potential or V is a scalar quantity. So VB equal to KQ over RB and VA equal to KQ over RA. Okay, so RA, KQ get cancelled out. So VB over VA equal to, can I say RA over RB? So I have RA equal to 1 mm, RA equal to 1 mm and RB equal to 3 mm. So it's 1 over 3. VB over VA equal to 1 over 3. The next one. Gauss's law provides a convenient way to calculate the electric field outside and near each of the following isolated charge conductors except a cube. You cannot, it is not easy, or this is not exactly right way of explaining this, but let me, Gauss's law is nothing but closed integral of E times dA equal to Q enclosed over epsilon naught. Okay, so we are talking about area. Area is, surface area. When it comes to the surface area of cube, probably you're talking about meter cube. Okay, so that could be the reason you can say we cannot apply Gauss's law for the cube, but there is a better explanation on the YouTube. Just type in Gauss's law for cube, you'll find a better explanation. But to remember, area is in meter square, cube is in meter cube. Just remember in that way. That's easy to remember. Okay, next one. A positive charge Q is uniformly distributed over a thin ring of radius A that lies in a plane perpendicular to the x-axis with its center at the origin, O, as shown in following figure. The potential V at point on the x-axis is represented by which of the following function? Okay, there is a derivation in my notes if you go through it, but let me take at this point, the Q charge is uniformly distributed all over the ring, right? Let me take this charge here is Q, small q. Okay, so small q is all over this ring. Okay, so V equal to KQ over the distance from here to here is nothing but square root of a square plus x square. So it must be square root of a square plus x square. Now this V is only because of charge here. Now what is the total V? Because of all charges, it's going to be, you're going to add everything, KQ square root of a square plus x square. So we need to add all the small charges. You will end up with, if we add all the small charges, it must be Q. So V equal to KQ over square root of a square plus x square. So Q equal to, it is uniformly distributed all over that ring, Q plus Q plus Q plus Q. So many Q's are in there. Okay, I'm going to stop here with these 3 quizzes. Next video, I'm going to go over the other quizzes. Thank you.